Good evening, BSKL Year 11. Thanks so much for coming along today. It's nice to see you all. Got 11 people waiting. 11. And a whole 11 people waiting before it's even started. I'm proper excited. Guys, thanks so much for coming. I really, really appreciate it. Today's going to be a tough topic. I think everyone in this room is probably thinking that they understand why they wanted to come along to this one in particular. Ionic and electrolysis. I'm really, really hoping that I'm going to make this a whole lot simpler for everybody, and hopefully have you all leaving this session thinking that you're able to tackle electrolysis better, and you're going to be able to tackle those exam questions with a bit more confidence, and you'll have a better understanding of what is occurring during the process. I'm going to really, really focus today on trying to make sure that I am covering all of the exam style questions and putting it into those contexts. Anyone who's got me as a teacher will know that I can rant. I could do 2 hours on electrolysis alone, just drawing awesome diagrams. But what I'm going to do is I'm going to try and really focus today on making this easier rather than more complicated. I'm going to try and simplify it as best as possible and have all you guys leaving feeling like you got a little bit of a better understanding, and that you're able to tackle those GCSE questions on papers 1 and 2 with a bit more confidence. Okay, so we've got 7 people now. A couple of people have ditched me already. That's very upsetting. Okay, so it's been really nice. I want to give a quick shout out to a couple of people. Sarah Lau has come along, and she's come prepared with questions for electrolysis. Thank you so much, Sarah. I really, really appreciate that. And you being prepared for this and having those questions that you really want answered. And all of those are going to be on the chat window for those people who are here. Thanks, guys, for waiting so patiently. Okay, so it's 2 minutes past 7. Let's see how we get on. And I'm going to start straight away. Can I also say apologies for not managing to get the video of me doing some of these practicals. I'm really hoping I've got to build a piece of equipment. I'm just going to show you a diagram of the piece of equipment I've got to build in this webinar. And hopefully you'll have a bit better understanding why I haven't done those. And I do apologize for not having done it sooner. Okay, questions are still coming in on the chat, which are really nice. What I'm going to do is I'm going to try and pick up some of those as we go through the lesson. Okay, so first thing I'm going to do, I'm going to share my screen so you guys can see what I've been up to. Because, of course, I have... Oh. So typical, my laptop. Oh, it's thinking about it. I think I definitely need to crank up my laptop as fast as it can be. Oh, it's thinking about it. I'm going to see if I can close some of these windows. Do you want to save changes? No. Oh, my Google Hangouts has stopped responding. Entire screen, yes please, share. Okay, we're there. Okay, so that means my face disappears, which always makes me feel a little bit better. Okay, so what I'm going to be doing, my usual thing that I've prepared for each one of these sessions. So my task today, I'll try and keep up the questions as best I can as well. But my main task today, I want to quickly run through an understanding. Anyone who has me in my learning objectives, U is for understand. So we're going to have the understanding of ionic bonding. And I'm going to put that ionic bonding into questions, ones that you're going to see commonly in your GCSE paper 1 and 2, both. Understanding of electrolysis. I'm going to try and link that to more to exam questions today. I'm going to try and steer away from going crazy and going into real depth on this, because you really don't need it for your exams. What we need to be able to do is we need to put this into context. Next one is be able to write the half equations. I'm going to make you all feel better with half equations, because I'm going to give you today every single half equation that they could possibly ask you. So that way, technically, you'll be able to learn this by rote rather than having an actual understanding of what those equations are. You can simply know what they're going to ask you and be able to just spit them out. It's not really what I like to do with chemistry. I think it's far better to have a good understanding of it. But I think that's a very good thing to be able to show you those. The last one is to know the exam style questions for electrolysis. Now, those people who are dual scientists in the room, I don't know whether or not I've got any, but when I get to that last one of the electrolysis, because dual scientists, you need to feel grateful here because you have no electrolysis questions on your papers because you only sit paper 1. So I thought I'd do something different as well today, which is what I have done is I have taken your specification and I've cut all the spec points regarding ionic bonding and electrolysis. My learning objectives to a slightly more in-depth level. So understand how ions are formed by the loss and gain of electrons. Next thing, know charges of these ions, group 1, 2, and 3, non-metals 5, 6, and 7. And do you know what? I want to make a point of this, which is this one. That one there, I'm going to, by the way, a usual thing, I have to fiddle around with different sizes of pens. But this one here. So these ions are ones that you just flat out have to know. You've got to be able to use these ions in all kinds of equations at various points. And these ones are worth putting onto a flashcard for you to learn. Silver 1 plus, copper 2 plus, iron 2 plus, Fe2 plus, lead 2, and zinc 2. Note that the majority of them are 2, 4 2s. Can I just emphasize, however, for electrolysis in particular, certain ones of these come up more than others. The first one is copper 2. Silver very rarely appears in electrolysis. I have seen questions over the years, but copper 2 plays a big part. And the next one is lead 2. It's very rare that you see the others, partly due to their reactivity and how the fact that their electrolysis products vary because of their reactivity in the series. And so what I want to do is I will come back to these two at various points through the webinar when we see some exam questions. The next thing I want to point out is your complex ions. Right, year 11, don't hate me, please, but you must know the hydroxide. And anyone who has me knows that I grill you on these at the very start of GCSE. My year 9s even know this now that they've started at GCSE. And I teach this as NOx. This is how I teach this particular method of learning. So we've got a nitrate ion of NO3 1 minus, hydroxide ions OH minus, carbonate ions CO3 2 minus, and SO4 2 minus. Now the reason why I teach NOx in this routine is because you have got the top 2 are both 1 minus, the bottom 2 are both 2 minuses. The next thing is the fact that carbonates are in position 3, and it reminds you of the CO3, and sulfates are in position 4, meaning it reminds you of the SO4. Nice just to bring that to light again. And in fact, the sulfuric acid one, the sulfate ion here, is going to appear in our webinar this evening. The next thing is write formulae and compounds for ions listed. Draw dot and crosses, that's going to be covered in today's webinar. Understanding of ionic bonding and the electrostatic. Understanding their high melting points and boiling points, and that's going to be Susan Boyle sings Nelly the Elephant. We're going to be running that, of course, today. We know that these appear so frequently now. And also know that ionic compounds do not conduct electricity. So this is bringing in the properties of ionics. So this here covers both. My Wi-Fi has just crashed. Donna, that's so unfortunate. Did I get a shout out? Oh, Donna. Sorry, shout out to Donna. I think she was the first person here. It was, no, Lucas. Lucas and Donna were the first people here, waiting patiently. I did like that. Thanks, Donna, for coming. Yeah, Susan Boyle sings Nelly the Elephant. Lucas is a great one. It's the boys. Yeah, no, yeah, it's definitely not the boys, Amira. But thanks for coming along. It's lovely to see you. Right, next thing is to drop into electrolysis. Please note that in your specification, this is done as bold. What this means is that this is for the triple scientists only. Oh, Daniel Booth, why have you got a sad face? Is it because it's electrolysis? It probably should be for that reason and no other. So we're just going to quickly run through some of these electrolysis points. Understanding covalent compounds do not conduct, mainly water. Cover that today. Understanding why ionic compounds do conduct. I'll bring that into exam questions. Anions, cations, that's panic. Anyone who has me as a teacher will know panic. I'll put that there. Describe the experiments to investigate electrolysis. Right, this one I loved picking up because they were very, very specific. They've got lead 2 bromide. They have got, I'm going to try and make this a little bit fatter. We've got lead 2 bromide. We've got and aqueous solutions of sodium chloride, dilute sulfuric acid. Year 11s, I have not done that with you in class. What that means is this is something new for even my class. And I've got copper 2 sulfate as well. Now, copper 2 sulfate is complicated because it comes in 2 forms. It comes in the purification of copper and copper plating. And predict their products, writing ionic half equations for them at the electrodes, and practical examples. So I'm going to be referring back to these points all the way through this webinar in order to try and make this a little bit clearer and make it as simple as possible. So already I've got, why can't you have zinc 1+ and zinc 3+ ions? Kai Kim, that's not E Kim, is it? No, it's Kai, I don't know, it might be. But I'm just going to call you Kim. Kim, do you know what? That's a very, very difficult question. And I'm happy to chat with you about that. It is A-level unit, AS unit 1, but you just need to know that zinc 2+ is the only one that you get. So stick with that's Kayun. Oh, nice, Kayun. So zinc 1+ and zinc 3+ do not exist. You just need to know that it's zinc 2+. I'm happy to give you some more details on that another time. Okay. So the first thing I want to do is I want to do the dual science and triple science section first. And what I've done is I've gone through the internet and pulled the pictures that I really liked. The internet is full of images of ionics, and do you know what? There were more bad pictures than good pictures. So the first thing I want to do is I want to come across ionics, and I want to just quickly chat to you about their structure, how they form, and the questions that you're going to see in regards to ionic. So, okay, so first one I want to quickly zoom in on is my very first image. So this image is a lovely picture. It was the best one that I found. I Googled the formation of ionic compounds and clicked image, and I got a whole load of rubbish. And this one was by far the best image. Now this image is so nice because the first thing to realize is in the specification, and I get to go back to this already at this point, you only need to talk about the outermost electrons. And it says here, draw dot and cross diagrams. This is point 1.4. It says, draw dot and cross diagrams. There we go. Draw dot and cross diagrams to show the formation underlining ionic compounds by electron transfer, limited to the combination of elements from group 1, 2, 3, 5, 6, and 7. And look, here it is in italics. Only outer electrons need to be shown. Now, by the way, Edexcel and all exam boards in their infinite wisdom do tend to break their own rules. So every now and again, they'll give you a pre-drawn diagram that you have to label with electrons. And if they give you ones with multiple shells, then you do need to include them. Do watch out. It's nice to do the reminder of 2, 8, 8, 2, because if you've got those numbers in your head, you can draw any electron configuration with relative ease. It's definitely something you should stick with. Okay, so I'll bear that in mind in a minute. I'm going to go back to my original diagram. So this particular diagram is the diagram of the formation. This is the question. This is where I'm constantly going to be juggling between my pen sizes. I do apologize for that. The reason being is I'm zooming in and out all over the place. This is the question of draw a diagram to show formation of an ionic compound. And in this case, it's sodium chloride. Everyone knows that this is the most heavily asked ionic compound. They like you to know about salt. And I understand it. It's a really good basis. It doesn't always appear, and I'll give you another one in a second. But this is to show the formation of NaCl. And the key bit here is the top diagram. So we've got sodium with, and notice, only the outer shells are shown. So we've got sodium in group 1 of the periodic table. I've suddenly realized I'm definitely at all points going to be needing my periodic table. So I'll have that on easy access. And we can see sodium here. Oh, that's definitely not what I wanted. I don't know how to go back now. Let's close that down and reopen it. So I've got sodium over there in group 1, and I don't know whether or not you can see me circling that. So I've got sodium over there in group 1 is Na, and in group 1, of course, 1 electron in its outer shell. I'm just watching my own webinar on my other laptop screen just to see whether or not you can see me circling the Na in group 1. I don't know whether or not you can. It's limited in terms of what you can see. I'm tempted to say, I don't even know. Oh, if I do snip on my screen, I'll be able to at least have access to my periodic table. There we go. So sodium over here in group 1 of the periodic table takes in the number of electrons in its outer shell. It's got 3 shells, shell 1, shell 2, and shell 3, and it has 1 electron in its outer shell. We all know that the number of electrons in the outer shell define its properties. So all those in group 1 are similar because of 1 electron in their outer shell. So if I go back to my original picture, we've got its 1 electron up there, and it's going to transfer, and this is the arrow. That's the mark there at your GCSE. Chlorine has 7. Now, of course, this picture is also limited. It's not entirely correct for a GCSE exam. In an exam, you would draw this as a circle, and you would draw the chlorines as crosses. We know that we need to show that they come from different people, and of course, they've done it via colors. Excuse me, 11. So the electron is being transferred from the sodium to the chlorine. The sodium is still limited to GCSE. We're going to put the Na in a square bracket and add a plus outside the bracket. The chloride, it goes from, this is chlorine as an atom, and then it becomes a chloride ion once it's gained its electron. And it now have a circle, and it would have its 7 crosses, only outer shell being used. But all of them are needed. You need the Cl, you need the circle, you need all the crosses and dots, but just the outer shell. So it's nice to see. I feel like I want to actually take that diagram and show you it redrawn somewhere else. So if I quickly find a space, just to show you this in an exam setting, I would put Na, I'd give it its circle with its cross. Now you notice that I've flipped here to cross. The crosses and dots make no difference as to who they belong to. I'm showing the chlorine atom having 7, and there's my reaction. So the sodium is going to lose 1 electron. So in terms of redox, it's lovely for me to remember and to recap oil rig at this point. Oil rig, of course, comes into ionic bonding, and it's kind of where it all begins. So what determines the charge on a transition metal? Winkit, that's really, really, really complicated. What you need to know is that the transition metals, A, can form multiple ions. 2+ is the most common. They all form a +2 ion because they all, and this is actually the important bit for GCSE, transition metals are all relatively low in reactivity. Why? Because they all have 2 electrons in their outer shell. That's because of the 288. As I said, requires a bit more depth then. I'm happy to do a webinar on transition metals at some stage. I use oil rig for oxygen, Lucas. Oh, well, I mean, you can use, right. Lucas, I get what you're saying there. Oil rig has actually got nothing to do with oxygen. It's all about electrons. Oxidation, oxy is loss of electrons. Bear that in mind. So the sodium has lost 1 electron, and this is going through oil. This is going through oxidation. And they would ask you at GCSE, explain why sodium is going through oxidation. And you would say, because it's losing 1 electron. It has nothing to do with oxygen here. No oxygen is even in the reaction, and it doesn't need to be. The chlorine, of course, is going through reduction. And reduction is the gain of electrons. And in this case, we've got chlorine that's gaining 1. So chlorine is going to gain 1 electron, and it's going to form its 1- ion. So we form now sodium. Metals are great. They're very simple. And we've got sodium becoming a +1 ion. Notice the outer shell completely vanishes. And the chloride ion, you still have to draw it. The non-metals are complicated, and you have to show their outer electrons all the time. So that's there. That's the final product. Sodium losing 1, chlorine gaining 1, and then forming opposite ions. And of course, opposite. This is one of the most important things in the whole of it, guys. This is one of the most important things in the whole of chemistry. Not Key Stage 3, not GCSE, not A level. This is just one of the fundamentally most important things in chemistry. Opposite charges attract. I cannot say how important that is. It haunts you throughout the whole of chemistry. And if you have a good understanding of that, then it really does make chemistry a whole lot easier down the line. Okay, so going back to my original diagram. So it's nice to talk about this and show the answer to that particular question. And I can say that that's done now. The next one, of course, in terms of Ionic, I've suddenly realized I think it's important to give a second example of this, because at times they don't ask you always about sodium chloride. So let's do magnesium oxide. Let's do magnesium plus oxygen. Now, I know it's in a pair, but in terms of the formation of its ions, we tend to draw them as single atoms. So we've got magnesium. Now, magnesium, of course, is found in group 2 of the periodic table. It's got 2 electrons in its outer shell. So I've got magnesium, and it has 2 electrons, and oxygen, of course, is in group 6. Going back to my table, oxygen over here in group 6. It's got 6 electrons in its outer shell. Notice how I draw them on. I draw 4, north, east, south, west, and then I put the other 2 on. And we can see that during this reaction, don't like that second arrow. During that reaction, the magnesium will transfer both to the oxygen atom. So the magnesium is going to lose 2 and go through oxidation, which is loss of electrons, lose 2 electrons. The oxygen is going to gain 2 electrons. So that's going to go through reduction. Reduction is gain, Rig. So this is Rig, and this is oil. And your final products, of course, are going to be Mg loses its outer shell entirely, forming a 2+ because it's lost 2 electrons, each electron being 1-, and the oxygen, of course, having to gain them. Notice that I draw it slightly different. I shouldn't. That's a really bad. Can I just point out what I've just done there is a very bad method. If I was going to do this again properly and I was practicing for an exam, what I would do is I'd still do north, east, south, west, 4, 5, 6. There's its own, and I then pair them up. By the way, a very common habit of students is to do this. Students really like to do this, and you're not allowed. That is, at GCSE, they'll probably allow it. In fact, I know they do allow it, but they shouldn't do. That's bad chemistry. The reason being is the electrons are going to pair in opposites. So that is not what I want you to be doing. I want you to be getting into a good routine, northeast, southwest, and then refilling it up again afterwards. So do bear that in mind. It's nice to see just to do one more. Magnesium metal, magnesium having 2 electrons in its outer shell. I'm going to do it with chlorine. One north, east, south, west. It's got 7 in its outer shell. Going back to my pick, chlorine, group 7. So chlorine then, of course, has 7, and one of them is going to go to the chlorine. But the problem is we're going to need a second one. North, east, south, west, north. Notice I changed my direction to make it easy for this. What's going to happen is I'm going to form Mg plus 2, of course, loses its outer shell, and the chlorines are left full. And again, I'm really sorry, Year 11. It's a really bad habit. Shouldn't do it. Northeast, southwest, fill them up to 7 and add your extra. And that's 1-. It's going to be the same thing. North, east, south, west, 1, 2, 3 extra, and 1-. So there's the final product of magnesium chloride. So the top picture, this picture here, I can zoom out a bit. This one, rub that out. This picture here, this here answers the very first question. This is formation. This is it being made. This is the transfer of electrons in the initial reaction. Show how the reaction's actually happening. Show the particles and how they transfer electrons. This is very common. And the final product, of course, is this one, showing them in their ion setting and having transferred them entirely, dot and crosses showing where they came from. Okay, going back to the next one. So I then got my next diagram. And this, of course, is one of the biggest leaps of faith required by GCSE students when you're doing compounds and how they react and the structures that are being formed. So ionic compounds, every single ionic compound, salt, magnesium oxide, magnesium chloride, calcium carbonate, calcium sulfate, anything that is metal, non-metal is going to be a giant, this is a gill. Oh, don't like that. Let's change that to a better color. This is a giant ionic lattice. This is a gill. I'm going to translate that as well. Giant ionic lattice. And the word lattice means organized layers. It's got a very organized structure. Okay, so I've got a question. Lucas, do you have to draw the circles on Na? At what stage or on the Mg? Does it matter which one has the dots and which one has the crosses? Donna, no. That makes no difference which one you do. Lucas, you asked me, do you have to draw the circle? Do you mean the shell circle? Because the answer, if you're talking about the shell circle, then no, you don't. When this becomes the product, you do in the transfer. Oh, I know. Okay, Lucas, I know where you've got this from. Okay. It's okay. Lucas, you can tell me whether or not I've suddenly picked up what you're talking about. Are you talking about doing something like this and how you can do oxygen like this? Right, this, I've just done it again, and doing it like this. And then doing, can I just say, Lucas, I don't like this arrangement. Some teachers teach this, and I don't like it. The reason being is it really doesn't make it clear between which atom is which and what electrons. And the oxygen, you can see the problem the oxygen is going to cause. Putting it in the shell means it's far clearer, and it makes it, and so the answer is probably not, but I would recommend for you to do it. It's good practice. Some teachers don't like it, and I'm a big advocate of showing their shells. The metals lose their shells entirely. The metals, of course, they have their shell originally, and then they, see, the problem is my X now isn't on the circle. So I'd do circle Na with its cross, and then that will become, and you need no circle whatsoever. Yeah. So I hope that's answered your question, Lucas, going back to up here. So it's nice to talk about these giant ionic lattices. Now, this has an impact, of course, on the question. They're going to ask, and I'm sure you guys will have seen this on the preliminary work that every single one of you has completed. The question that comes with this, of course, is explain the high melting point. This high melting point or boiling point makes no difference. And this, of course, is whenever you see this question, guys, it needs to be, as soon as you see melting point and explain, you're running Susan Boyle sings Nelly the Elephant. Yeah, and what we're doing is we're running structure. And this gains you all the marks. Don't shortcut this year 11. Don't skip any of it. Do it all in its entirety. Structure. This is a giant ionic lattice. And no, you're not allowed to write the word gill. Next, bonds. So these, now this one's tricky. Right, year 11. You are allowed to write ionic bonds. But please don't. I do not like this. You are setting yourself up for a fall. You're going to see this in the preliminary work, and I really don't want you to be doing this because it's bad chemistry. What the correct answer is, and I'm going to ask Amira, can you give me the correct answer, please, for bonds? I'll give you a minute just to, I know that there's about a 15-second delay. So if you could, Amira, just quickly type in the correct answer for the bond mark, please. Now, while Amira is responding to that, I get an opportunity here to drop into the preliminary work. And what I want to quickly point out here is, let's see if we can find it. There was a question somewhere. Oh, I'm really hoping it was on this. It's so not going to be, is it? Oh, that's so typical. The electrostatic attraction between... Thank you, Amira. Yeah, outstanding. Great job, Amira. You've got one... I'm going to make a note. Amira, you've got one commendation right there. Outstanding. I'm making a little note on my commendations. Oh, I made a mess of that. Is it double M? I don't know. Commendations. Is it double M? Is commendations or double M? Commendations. Commendations, Amira. Well done. Great job. One for Amira so far. They'll continue to increase. So we've got... So she's absolutely right. It is the correct answer to this is the electrostatic. Please, folks, electrostatic attraction. And yes, I know it's a lot of words, but please, I know that lots of you are going to be taking A-level chemistry, and this will hold you in good stead. The electrostatic attraction between oppositely charged ions. Well done, Amira. Charged ions. Great job. I've also gone and draw the whole process. I've also gone and stolen a whole load of other questions from exam papers, and I think this is maybe where I saw it. There, guys. So I've pulled this one. By the way, I looked back through 2017, 16, 15, 14, 13's papers. And what I want to show you here is the fact that I'm pulling lots more questions rather than the preliminary work. I thought it'd include some others. State what is meant by the term ionic bond. Now, a mirror has just given me the perfect answer. What is meant by an ionic bond? It is the electrostatic attraction, electstat, between opposite charge ions. There's your answer. And so it's nice for us to see that that question is a thing. So please make sure, I want you to be using good chemistry here. I don't want you to be using cheat chemistry because you find it easier. Stick with good chemistry. It will hold you in good stead. Okay, so it's nice for me to see another exam question. These, of course, are all real ones from GCSEs. So the next one, of course, we've got bonds, and then we've got strength. So the next one is strength, and we know that the electrostatic attraction is Wellard, like me. Like Mr. Duncan is Wellard. So it's a very strong attraction. This is the number of bonds, and it is millions. Now, of course, this, comes back to this diagram, which is this diagram shows how many bonds there are going to be. This is in a giant structure. Anything giant, year 11, is got millions of bonds. Now, I'm going to make you all feel a little bit happier. I get to drop into bonding in general just for a minute. So just to drop into bonding just for a minute, we know that in bonding there are 4 types. We've got ionic, and it's giant. We've got metallic, which is giant. We've got giant covalent. I really don't think I need to sing the giant, but giant. And then I've also got covalent, sometimes referred to as simple covalent. And this is the only one that is small molecules. Irrelevant question, is there an electrostatic attraction and metallic bonding between the cations and electrons? Kayan, of course there is. In fact, metallic bonds are the electrostatic attraction between the giant lattice of cations and the sea of delocalized electrons. That is the metallic bond. Absolutely. That's why it's strong. That's why metals have melting points in the hundreds and the thousands, because that bond is strong, that attraction is strong. And yes, of course, it's nice to see you make that connection. That's lovely. Last point is energy. You cannot leave this question without talking about energy. Lots of energy needed to break bonds, break all bonds. Nice to say all bonds. So nice to see the question being done. It's nice to see the picture. They form into these giant structures. Dinesh has made an appearance. I love it. Oh my God, it's boss. It's Dinesh. And for covalent, it's the electrostatic attraction between the shared electrons and the 2. Yes, that's correct, Kayan. So when they ask you, so the first thing is they ask you 1 mark, what is a covalent bond? The answer is a shared pair of electrons. Covalent is WIMF. No, Amira, it's not. It's not. Covalents are within the molecules. The WIMFs are between. Just to quickly do that. In water, these are covalent bonds, cove bonds, and they're Wellard. But what's between the molecules are WIMPs. You have covalent within them and WIMPs between. You don't break the covalents. You break the WIMPs. I'll come back to that. I'm doing a covalent webinar. Don't worry, folks. Later on. Okay, so at that point, we've covered the main questions regarding ionics, the formation, the ion formation, and the dot and cross diagrams, otherwise known as, by the way, Lewis diagrams. Dots and cross are called Lewis. Now we drop into another very important property. I found this really lovely picture. I really like this picture, showing that when they're in their giant structures, they don't conduct electricity, hence no light. Yeah, there's no light on. Now, the reason for this is because, and it gave you a really nice answer, the positive and negative ions are fixed in a solid and do not conduct the current. The ions are locked in position, ions fixed in position, and cannot flow, cannot move through the structure, So that's as a solid. So solid salt does not conduct. However, if you melt it, if you melt this, by the way, this point, I'm going to attempt to use one of my pieces of software. I don't know how well this is going to work here, 11. We will give it a go. That's if it decides to work at all. There we go. Right. It's going to be interesting to see how well this works. If I drop this into Ionic. Oh, can I? Yes. Ionic. Where's Ionic? I'm going to have to react it first. Just... So when we have our ionic solids, are incredibly tough, very high melting point, giant structures, a lattice, and this is what's happening in this video, in the short animation. So this is a metal reacting with oxygen. So the metal starts off in a giant structure. The oxygen is a simple covalent molecule. When they react together, they form this giant ionic lattice held together by the electrostatic attraction. You'll notice, even at full temperature, it's not a liquid. However, if I keep increasing the temperature, it will eventually become a liquid. Now, I can't, unfortunately, with this. So I can't. This animation is limited in how well it works. So if you heat it up to the point where, I don't know if I can do, if I just warm this up, when it becomes a liquid, the ions are able to move over each other. And because they can move over each other, they can carry the charge through the structure. What if you had an insoluble ionic compound in water? Would that conduct electricity? No, not at all. Because you're just going to have a lump of ionic solid sitting at the bottom of water, and there will be no free ions. What is distilled water? Lucas, that's a really lovely question. Distilled water is commonly called, another name is given to it, is deionized water. Distilled is telling how you made it. You boil the water. You can melt it only, I think. So anyway, if you distill water, if you boil it and take the liquid, you'll leave any ions behind. So you end up with water with no ions at all. What that means is distilled water is the epitome of pure water. No ions. No ions. So what that means is pure water will not conduct electricity. Pretty sure it won't. It wouldn't be aqueous. Mixture of solid and liquid. Absolutely, that's correct. Juyi, spot on. Okay, going back to this. So what I want to now do is pick up some of those questions that we commonly hear. So they commonly ask you to explain why it conducts. So I'm going to put this. I want to see if whether or not I can come across. There we go. So here's the question. Explain why the electrolytic cell containing lead bromide needs to be heated before electrolysis can occur. So you would say before heating. Before heating, lead bromide, PbBr2, is a solid, and ions cannot move. Cannot move. How are we doing for time? God, it's gone fast. Ions cannot move. When heated, solid lead bromide will melt, allowing ions to move and flow through structure. Now, people often say to me, how is that worth 2 marks? The answer is it is. The fact that it's worth 2, it should be worth 3. But just be careful. Isn't pure water called deionized water or something? Yes, Amira, deionized water is the same as distilled water. That's what Mr. Duncan said. Dunking. Hey, I'm the king. Sorry, we'll get distracted. Anyway, so going back up to here to my, I've got to get crack on from Ionic and then onto electrolysis. So pure water, note the picture. Pure water, no ions. There are no ions in here. No ions. So it will not conduct, and we see no light on. Water, distilled water, deionized water will not conduct electricity. There are no WIMPs in ionics bonding, right? Yes, Amira, there are no WIMPs. None. WIMPs is simple covalent only and graphite. So when it's a solid, the ions are there, but they're not able to move. Look, when it's in solution, when we put salt into water, if I go ionic and I go fast, you're freeing the ions. The ions are being pulled apart by the water molecules, and they become free to move. So you can see what's happening here. The ions are able to move around freely. What that means is if I stick in electrodes here, the positives are going to go to the negatives. Lucas, what is WIMPs? Weak intermolecular forces. It's just an easy way of practicing and remembering weak intermolecular forces, Lucas. That's all. So the ions become free to move in the solution. As a solid, they're locked in position. They're locked at the top. But once in water, they're free to move around. Hence why salt water conducts electricity. Because the ions are free to move to carry the charge through the structure. They do love those questions. Okay, so that brings us to the end of ionics. So I'm going to do one more thing, which is their brittleness. I can honestly tell you that in my 10 years, slightly longer, 10 years of teaching, this has only ever appeared once at GCSE in my time. And they gave you this exact diagram. And what they wanted you to do was to explain why, when ionics are struck, why is it that they shatter? And the answer is, what you just had to say was, before the ions are opposite charges are next to each other. And then when you move them, like charges are next to each other, which means you get the mark for saying at that point they're going to repel, and so they break. This is what makes ionic compounds brittle. Okay, so it's nice for me to cover all those. Okay, at this point we get to drop into electrolysis. Right, the first thing I needed to do was to show you this diagram. This diagram is one of the most important diagrams for GCSE in paper 2. Right, so any dual scientists that are there, you technically don't need to be here for this. So anybody there can disappear. I'm giving you permission. But those people who are doing paper 2, I'm going to delete that. There goes Susan Boyle. Okay, and I'm going to go back to this diagram. So this diagram is one of the most important because this is electrolysis of solutions, not melts, but solutions. This here is a solution, and there are several they can give you, but the one that they always tend to ask, in fact, there are 2. Number 1 is they're going to ask you to do brine. Now, brine is the common name for sodium chloride aqueous. This is just flat out household salt water. This is the most common. So when you see this diagram, they can give you this and they'll ask you to label it. Well, the first thing is, do you notice the ones at the bottom? So these guys, people often get these wrong, but they're pointing at the electrodes. And people often get these wrong. So we've got panic now makes an appearance. And we have a positive anode. Oh, positive. There it is in the diagram. There's my battery. There's my positive. This electrode is called the anode. 1 mark. Next one, negative cathode. It's a nice way to do it. I quite like panic. I didn't invent it, which upsets me. But it's quite useful. So this one is the negative electrode, and this one is going to be the cathode. They are commonly got backwards. I tend to find that students seem to go full on 50-50 on this, and I really don't like 50-50. Folks, you should never guess chemistry. So panic's a good way of remembering it. Right, next thing. So now that we've labeled that, they're now going to say, what is this? And we call this the electrolyte. The electrolyte is any liquid that conducts electricity. Molten salt, liquid, molten and liquid mean the same thing. Molten salt, any solution that's ionic is going to be an electrolyte. And in this case, sodium chloride aqueous. Okay, we now get two gases. So I now need to do electrolysis of brine. So the electrolysis of brine, and at this point, I'm going to give you all the half equations to learn, and I will do a summary half equations as well. Electrolysis of brine, and I'm going to keep this short, folks. Okay, so the first thing is we get three products. We get hydrogen gas. Okay, so why do you get hydrogen gas? The reason being is in the sodium chloride solution, if I zoom in as far as I can, we have got a liquid here. I'm going to zoom in. My year 11s are going to know these pictures. In that water, I have got sodium plus from the salt. I have got Cl-. This is a cation, by the way. Sodium cation. That's a cation. We've got an anion over here. So a chloride anion. But from the water, we also have H2O. But because of that, we also get H plus and OH minus. So we have we've got four, we've got two, and look, I've highlighted them in different colors. Two positives and two negative ions. So when you do brine, you get hydrogen gas. Why? Because the H pluses will move towards the electrode. Here's our negative electrode. Here's our positive H plus. It will move towards it and it will strike it. I'm going to move it over there. The H ion moves over, it hits it, and it will gain back its electron to form a hydrogen atom. And at that point, it will pair up. So it's going to gain an electron and form H2. I'm going to now balance that. Two H's. Learn that equation. Do ions carry charge? Yes, Dana, they do. More importantly, the negative ions carry the charge. But actually, do you know what? That's actually not important. The ions carry the charge, Dana. That's a great thing to say. How long do the webinars usually last? An hour, hour and 15, Aaliyah. Okay, so hydrogen gas forms. It's the first product of the electrolysis of brine. Next, right, at the other electrode, I form chlorine gas. Okay, so I have the Cl minuses. The Cl minus ions are going to strike the electrode, and they've got an extra electron. Look, northeast, southwest, put them on circle. There's the electron that wasn't hers. She's going to bump into that, and she's going to give that electron to it. And that electron zips up the wire. And chlorine becomes, so the chloride ion will become a chlorine molecule. And it will lose electrons. Balance it, two chlorides, two electrons. So those are your first two half equations. I'm going to list all the half equations you're going to need to learn at the end of the session. But there's that one. The last product. So we've got two products, chlorine gas, hydrogen gas, and we get one more product, which is the ions left over. So I have just turned this into chlorine gas, Cl2. I've just turned this into hydrogen gas, and these guys are left. So my third product is sodium hydroxide. My third product is NaOH. So NaOH aqueous. We form a sodium hydroxide solution. Three products. And that's because the ions are just left in the solution. So the whole thing becomes alkali, and it turns purple in universal indicator, pH 14. So, okay, I just want to quickly do something else here, which is I just want to do a quick list. So we make products. This is something, if you want to make notes, folks, this is something you should have. My year 11s, you have these in your books, but you might want them again. Products of brine. Oh, that didn't work. Brine electrolysis. Electrolysis. And they are hydrogen. Right, it's a fuel. It's used for, it's used for hydrogenation of vegetable oils to make margarine, but I don't really want that. Fuels. It is hydrogenation. That's annoying, that. Hydrogenation of veg oil. Rare one, it never appears on Edexcel. Oh, God! Manufacture of ammonia. Making ammonia. Oh, my God, most important one. Making ammonia. Yeah. So next one is chlorine. Chlorine is used, sterilize water. Sterilize water for making bleach. It's used in the manufacture of bleach. And for making PVC, which is a type of plastic. Next one, sodium hydroxide, NaOH. This is cleaning products, and used in the making of soap. So 3 products, and they love these guys. PVC for water pipes, right? Yes, absolutely right, Lucas. Margarine is yucky. Yes, it is. PVC for water pipes, sure. Yep. I mean, water pipes in the house tend to be made of copper, but the ones for your guttering on the outside of the house tend to be made out of plastic. But yes. So PVC plastic. Okay. So I'm going to now come back to the same diagram because, guys, at this point we can continue to label it. I'm going to make this bit vanish. Right. So now we can now list our products. So we now know that this here is the negative electrode. This here's the negative side. This is negative and this is positive. Right, which one appears where? So what's going to happen is the positive will attract the negatives. I'm going to get chlorine gas here. That little one is chlorine gas. And on the other side, the negative electrode attracts, this one attracts the positive and this one attracts the negative. So I'm going to form hydrogen gas over here. Guys, notice the volumes of gases are different. So I need to explain this. So the reason why it's different is because chlorine gas, we know, is soluble in water. It's soluble in water. That's why we add it to water to kill bacteria. So the reason why the gas is not here is because the gas itself is dissolving into the water. So you're forming chlorine water, by the way, which will bleach stuff. And over here, we've got hydrogen gas, which is insoluble in water, or has a very low solubility anyway. Solubility is low. So we've got more gas here than we do on this side. This question comes up regularly. So I'm going to use the same diagram. At this point, we're done with brine. Let's get rid of brine. And at this point, I go back to the spec point. There is one other similar experiment we use, and that is for sulfuric acid. So now we're going to do the electrolysis. And again, if you want notes, they're useful. Electrolysis of sulfuric acid. So sulfuric acid, the first thing to realize is what the ions are. What would it look like in the solution? I would have H plus from the acid. 2 of them. Loads of those guys. Since brine is a solution, is there any chance that small amounts of oxygen will form at the anode? No, you don't get any oxygen. You're going to ask me why. Would you get small amounts? No. I want to say no, but chances are you're going to get tiny amounts of oxygen, but you definitely don't detect it. If you burn the hydrogen, it burns as if it's pure hydrogen. There's no oxygen there. So no, I'm going to say no to that question, Juyi. Good question. There are times when 2 reactions will take place, and they did it. Edexcel did it. They were really mean. So Juyi, I'll accept it, but it's so rare. It's a bit annoying that they asked it. I'll come back to that question. I think I got it on the webinar. I've also got SO4, 2 minus. NOx, 4th one down, 4 S's, 2 minus. What else do I have? H plus from water. And I also have 1 more ion. I've got OH minuses. Please note, I have only 1 positive ion. They're all the same, which means in the electrolysis, of sulfuric acid, I will only have hydrogen gas at the negative electrode. So I'm going to make hydrogen gas again. This time, water won't do anything. Why? Because it's electrically neutral, and so it won't go to the electrodes at all. But I now have two ions, and one of the ions will go through the reaction and one of them doesn't. And the answer is it's the OH minus ions that do. The sulfate ions are much larger. They don't tend to make their way over there quite so quickly. And the OH minus ions are able to be decomposed more easily. So I could look at it in terms of reactivity, but it's not quite as straightforward as that. So the ions never move to the electrons. Do OH minus ions like never move to the electrons? Yes, of course they move to the electrons. They move towards the positives. So they'll group around it. I'll end up with all my OH minuses just grouped and waiting around the outside of my electrode like this. So what's going to now happen is, and this is one of my other electrolysis half equations, the OH minus ion is going to hit the electrode and it's going to form oxygen gas and water. Now we need to balance for this, I'm pretty sure. So, okay, we need two H's, right? So at that point, I've got two O's, I've got two H's. Now I've got two H's, but three O's. That's awkward. If I put a half there, I get one O. That works out. Now I need to balance for charge with two electrons. I need to shrink this down, folks. I'm going to shrink that down so it fits on my line. So I have got OH minus hitting the electrode and becoming oxygen, gas, and water. It rips it in two. I'm going to need, now I put a half in, I'll get rid of the halves. 4 of those, 1 of those, and then 2 of those, and then 4 electrons. Guys, it's a very rare equation to get, but it does every now and again appear. And I'd recommend just flat out learning it. I'm going to give you the summary list in a moment before I go on to the questions. But I get hydrogen as normal, and I get the OH minus. Right, at this point, I now need to cover another piece of equipment. This here is called a Hoffman voltammeter. What a disgusting piece of equipment this is. And this whole thing is designed to be able to show the products of electrolysis. We have our 2 electrodes down here. This is the positive electrode. This is the negative electrode. I'm going to fill the whole thing. I'm going to fill the whole thing. Fill the whole thing with salt water. And then what's going to happen is the gas will collect. I fill the whole thing up with it like this. And you add a bit of universal indicator. And what will happen is the gases will collect up here. They'll collect in these regions. And then you can play around with the gases. It's not particularly complicated. It's just every now and again the pitch appears and it freaks people out. So don't overthink it. I'll see if I can find a question towards the end. Okay, next. Right, we're not finished with the electrolysis, I'm afraid, folks. Because what examples of electrolysis do we have? So we now need to do the examples of electrolysis. Now, just to make you feel better, there aren't that many examples of electrolysis. And people think that there are millions. There aren't. So the list is, number 1, brine. Top answer. Asked more than any other. Second one, the electrolysis of copper sulfate, CuSO4. Now, copper sulfate, this can have 2 places. It can be plating. Might see a question on that. Plating or purification or purifying. So 2 places there. Next one, lead bromide, PbBr2. And this is going to be molten. This is going to be solid, but they're going to melt it and it's going to become a liquid. This is aqueous. This is aqueous. This is liquid. Molten example. They love their moltens. And the last one is sulfuric acid. There aren't that many. There's only 5 examples if you include copper as the 2. What that means is we can write down every half equation you will ever get asked. Let's write them all down. Let's do brine first. So this is the summary list. summary list of half equations. That you will need in your exams. And you can just learn these, folks. Electrolysis gives me anxiety. I know. What's the half equation for the sodium hydroxide? Well, the sodium hydroxide has no half equation because no reaction is happening. It's just floating around in solution as its ions. They don't change. Also, like if there are OH minuses around in the positive electrode, does that make the area more alkaline? Yes, Kayun, absolutely. The first in the, oh, what a lovely thing. This is where I really wish I'd done the bloody video. Guys, if I'd done this video with the Hoffman, and I've got a Hoffman in school, okay, year 11, if someone wants to come and help me out, tomorrow lunch, maybe not tomorrow lunch, maybe tomorrow break time, if somebody wants to come and help me set this up and do it, then I will happily show this and videotape it and put it on YouTube. But Kayun, yes, the side that goes purple first is this one. That goes purple. It goes purple immediately. And this side bleaches. This side gets bleached white. It gets bleached. This is where I wish it was darker. Bleach, 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 yellow, yellow. It's bleach, bleach, bleach. I don't know why it's not working. Bleach, 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 bleach. It gets bleached because of the chlorine. The chlorine bleaches it. One side goes purple, one side goes yellow, and the bottom, right down here, we tend to see like this cool divide line where it's getting pulled off to the two sides by the gases. Kind of nice. And the top tall tower remains green. So it's a cool thing to see. Right, list of summary half equations, folks. Every half equation they could ask you. First one, hydrogen. H plus, two of them, gaining 2 electrons to form hydrogen. They could ask you that one. Very common, very likely. Next one, you can also have Cl minus, 2 Cl minuses going to Cl2 and 2 electrons. Next, you can have oxygen. Aluminium electrolysis. I've just suddenly realized there's another example. Oh dear, I've missed an example, folks. There is another one. The other one, where did I put my list of ones that they can do? Oh no. Oh, there. The other one they can do is aluminium. They can also give you aluminium oxide molten. Extraction of aluminium cryolite. So you can also have O2 minus, 2 of them going to O2 plus 4 electrons. They can also have aluminium appear, aluminium 3 plus, gaining 3 electrons to form aluminium. Notice this isn't hard, guys. There's patterns. We've also got OH minus appearing. This is a very rare one, very hard. 4 OH minuses going to oxygen gas, 2 H2Os, and 4 electrons. People often ask me where the 4 electrons come from, because I've got 4 minuses. So in each electron is 1 minus. So I need 4 of them to cancel it out. If you go through all the papers, you really can't go wrong with this, folks. Is there any other equations you could get? Yes, you can get lead and bromine. Lead, Pb2 plus. You've got to remember that from the ion list. Gains 2 electrons to form lead metal. And you've also got bromine, Br minus, going to Br2. And that is all the equations. And guys, there's 7. That's not as many as you think. Oh, copper. No, 8, sorry. Copper 2 plus, gaining 2 electrons. Copper 2 plus, gaining 2 electrons to form copper metal. In the plating, so yeah, in the purification, it can be reversed. Because in the purification, you have 1 electron get fat and 1 electron get thin, because you're going to move the copper across. It's one to mention, actually. So in the purification of copper, we have a pure pink, a pure, that's rubbish. Give me a wide one, as wide as possible. That really doesn't help me at all. A pure, I don't like it. I don't like it at all. Let's go for it. Don't like it. Oh, it's just not very nice, is it? It won't let me do it. Plus, 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 plus. It won't let me go any bigger. Pure copper. Pure copper here. Oh, actually, they tend to go the other way around. Not that it matters. This is pure copper. Pure copper. And then they have impure copper. And this is impure copper. And notice it's bigger. This electrode is big. And it's full of impurities. And there's one impurity more than any other. And that's carbon. So it's full of carbon impurities. Now what we want to do is we want to move the copper from one side to another. And the way that we do this is, number one, you need an electrolyte with copper in it. So we choose copper sulfate. Link it up to a battery. Now I want to move copper 2+ ions towards this electrode. So I need to make that one the negative one. So the negative electrode there, and that's the positive. So what happens in this process, if I zoom in, what's happening is the copper, if I zoom in, I'll be quick, folks. If I zoom in here, the impure copper 2+, full of carbon and other junk. These copper atoms. It's not going well. These copper atoms hop off. I've just made an O, of course. I'll get rid of that. These copper atoms hop off into solution. The battery rips their electrons off, and they hop into the solution as copper 2+. Let's look at the half equation. The copper becomes copper 2+, and it's going to lose 2 electrons. Next, for the equations involving H+, how do you know which ones happen and when? So H+ pretty much always happens except when silver's around. OH- happens, of course, in sulfuric acid. That's and that's it. It's the only time. OH- only occurs with sulfuric acid. So just remember that one. Good question, Kayan. And on the other side, the copper now makes its way over to this electrode, and it recollects its electron. So it turns from copper 2+, it gains the electron on the other side, and turns back into copper. So it leaves here, goes into solution, and then gets put back onto here. So this one gets thicker, and this one gets thinner. And you end up with a sludge at the bottom of here, which is all the impurities. So it's every now and again. Let's have a look at some questions. That actually brings me to almost the end. I haven't done aluminium, which is frustrating. I've done it for an hour and 4 minutes now, folks. I do apologize. I just want to make sure that I cover aluminium in its extraction. Aluminium is only special because it involves cryolite. They take the aluminium oxide, they melt it, they add cryolite to it to lower its melting point. And I've given you the half equations. Right. I think at this point, I want to do some questions you haven't seen yet. Right. So now Edexcel, like if you electrolyze H2SO4, that's not an acid. So if it was molten, what do you get? Juyi. So, okay. Sulfuric acid, you can electrolyze concentrated. It doesn't conduct electricity. The reason why acids are only acids when in water, which means if you don't have water, the H2SO4 doesn't break up into its ions, which means it doesn't conduct electricity. Does that answer your question? No, it doesn't. Okay, Edexcel. Guys, look what they did. They put everyone together. They got solid lead bromide. Oh, I'm going to delete that. It's too black. We got solid lead bromide. We've got brine and copper sulfate. Oh, how evil's that? So this guy's positive. Let's first of all start labeling it. First thing, let's do red. Here's my red positive. So that guy's positive. That guy's positive. That guy's positive. So one on the left. They're in series. Therefore, negative. This guy's negative. Negative, negative, and negative. Right. What's going to happen? Number one, name the particles that move through the connecting wires to form an electric current. Right. They're wires, guys. Wires contain metals. Metals have delocalized electrons. The electrodes are made of platinum, which are an inert metal. State what is meant by the term inert. So if it was molten sulfate salt, okay, Juyi, I get why you're asking it. Okay. The sulfate ion will be decomposed. That will be ripped apart, and you will make oxygen still. You'll make smaller sulfates, SO3 2- instead of SO4, and you'll form O2. You'll start ripping the SO4 2- apart. You will. You won't ever see the equations of GCSE. But great question. Oh, right. Right, guys. I'm blocking them. Report. And I'm removing the person who's used my name. They are being removed immediately. Put user in timeout. Hide user on this channel. It's gone.
Report user.
There you go. Right. I hope that helps you. All right. Next. So why are the electrodes made out of platinum? Stabilize. Remember the word inert. Inert means unreactive. That wasn't me. Okay, that's fine. No problem. I believe you. Okay, going down to here. Right. Juyi, you asked this, or was it Juyi? Somebody asked if you could get both. You will. So when sodium chloride is electrolyzed, two gases form at the positive electrode, one of the gases at the negative electrode. Name the gases. Right. Positive electrode. Positive electrode will attract negatives. So I'm going to get chlorine gas and oxygen gas from the OH minus ions. Next, what are we going to get at the negative? We're only going to see hydrogen at the negative. Opposite charges attract. Yeah. Next, give the Ionic a half equation to show the formation of each of these gases. H plus goes to H2. Balance gains 2 electrons. Right, next, chloride goes to chlorine. Balance 2 electrons. OH minus forms oxygen gas and water. Balance with 4, 2, and 4 electrons. Guys, knowing them helps. Just speeds things up. I know it sucks, but it's worth knowing. Next. Stay always meant by the term ionic bonds, electrostatic attraction. Here's my electrolysis of brine. Again, what is meant by the term electrolysis? To split. The word lysis. The word lysis means to split. To split using electricity. Not complicated. Not complicated. Next, identify the gas A, B, and solution C. So negative electrode will attract positives. So I'm going to be getting H plus. Gas B is hydrogen. Positive electrode is going to attract the minuses. Gas A is going to be chlorine. And the solution at the bottom is what's left over, sodium hydroxide. We get this over and over again. Make sure you learn it. Why does sodium chloride have to be molten before it conducts? So the ions are free to move to carry the charge through the structure. Write an ionic equation for chlorine from chloride. Chloride going to chlorine. 2 of them, 2 electrons. So we get that there's repetition here, folks. Over and over. Same repetition, and it's good to see it. Right. Let's go to our preliminary work. Okay. So question 1. What is nice and easy? Not ionic and electrolysis, but just simple chemistry. Exothermic, a reaction that releases energy, heat energy to the surroundings. And I just gave the symbol as well, which is minus delta H. That's a delta, by the way. It's a triangle. Delta H for enthalpy, negative enthalpy. Next, select your oxygen atom, 2,6, and we get D. Notice the electrons. We've got 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons in total, 2,6. Too many electrons. There's a noble gas. Too few electrons in the outer. In fact, oh my God, what the hell is going on there? Like, what? 4 electrons on that. No. Don't think so. Losers. Next. Oh, magnesium ion has lost 2 electrons. Give the charge on, show the structure of an oxide ion. So we've got 2 electrons in the first shell of all of them. That's correct. That's nice to see. Tick, 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 and tick. Next, we know that oxygen is going to gain 2. And it's going to fill its outer shell. And it's going to become 2 minus. So A was the standout answer. This is 1 plus. No. 2 plus. No, it's not a metal. And 1 minus. No, that would be in group 7. So nice to go through our ion structures. Next, guys, nice to remind you again. As soon as I see, in terms of structure and bonding, explain high melting point of magnesium oxide, MgO, metal, non-metal, it's ionic. Sound like a minion. What? No, I don't know what you're talking about, Amira. I heard that too. No, definitely not. So Susan Boyle sings Nelly the Elephant, giant ionic lattice, electrostatic attraction between oppositely charged ions. This is a very strong attraction. There are millions of attractions, lots of energy needed to break. 4 marks. Don't skip it. Formulae and name, sodium magnesium chloride, and formula MgCl2. Next, question 2. Okay, one of the tough questions. Water is formed from 2 atoms of hydrogen combined with 1 atom. Draw a dot and cross for the water and show the electrons in the outer shells only. Next, explain how the covalent bond in water is held together. So this wasn't ionic, this is covalent. So I drew the diagram. H2O, water in the middle, single bonds either side. Covalent bonds are a shared pair of electrons. Should always say that as point number 1. It is the electrostatic attraction between the shared electrons and the 2 nuclei. Just to explain that in the diagram, here is the shared pair of electrons. Don't like red. Here is the shared pair of electrons. And here is the nuclei in each one. Here is the nuclei of each atom. And it's the electrostatic attraction there that holds a covalent bond together. Next, they did exactly what I said they'd do. Configuration of sodium atom, sodium oxide, describe in terms what happens when it is formed. Okay, so here's my diagram. Sodium is going to lose 1. Oxygen is going to gain 2, 1 from either side. And there's my outcome. Those diagrams get me nearly every single mark. In fact, it does. It gets me all 3 marks are there. Sodium loses 1, oxygen gains 2. So 2 sodiums react with 1 oxygen. Oil rig there going on again. State 1 reason why the reaction is described as an oxidation. Oil rig. Oxidation is loss of electrons. Who's losing? Sodium. Metals lose. Oxidation is loss of electrons. Sodium loses 1 electron. That would be 2 marks in terms of my answer, but 1 mark. The answer is just oxidation is loss of electrons. Sodium loses. It's nice to have the detail. Next, explain why water has a much lower melting point of sodium oxide. Sodium oxide is ionic. Water is simple covalent. Water molecules have WIMPs. You're not allowed to say WIMP in your exam. So I can draw that for that question. Lucas, of course you can. Of course you can. But drawing diagrams is hard. Most people don't know what the heck they're doing. Most people think that chemistry is in Hebrew. Let alone being able to draw a diagram. If you can draw a diagram, they will mark it all day long. Absolutely. Next, water molecules have weak intermolecular forces between the molecules, less energy to break than the ionic bonds. Notice, I hate that. Less energy to break than the electrostatic attraction. Let's be good. Electrostatic attract between oppositely charged ions. Next, right. A teacher adds sodium oxide to water. It reacts, add your state symbols. That's ionic, therefore solid. Water is always a liquid. And sodium hydroxide will be aqueous. Next, they do love their state symbols. What color would it be? Universal indicator coming back to haunt me. We know that the universal indicator needs to be purple for sodium hydroxide, not blue, year 11. Purple, pH 14. Ion responsible. OH minus is what makes something alkali. H plus is acid. That's what makes an acid an acid. And what makes, and OH minus is what makes an alkali an alkali. So there, and of course this is alkali purple, so OH minus ions. Next, calculate the relative formula mass found on the periodic table. Add them together, 40, nice and easy. Give the formulas of the 2 ions, Li plus and F minus. I like it. Right, hardest question on the paper. Compare. Explain why the ionic compounds have high melting points. The ionic melting point of magnesium oxide is much higher than that of lithium fluoride. So we need to explain why. So now the great thing is we get all the first one, ionic compounds have a high melting point, because we get that with the electrostatic attraction in the latter. So lithium fluoride is 1 plus and lithium 1 plus and lithium fluoride and Mg2 plus in magnesium oxide. I've compared the 2 positive ions. Next, I then compared the 2 negative ions. And you'll notice there is a bigger difference between them. I have got a 2 plus. I'm going to do this in red. I have got, if I just go for a charge line, here's 0. I have got +2 over here and -2 over here. A gap of 4. Strong attraction. Their opposites attract. With this one, same line, but now I've only got +1 and -1. I've got a difference of 2. The strength of that bond is half as strong. The strong electrostatic attraction, more energy. So bigger difference in charge means a stronger electrostatic attraction, more energy needed to break. Explain why ionic compounds do not conduct electricity when solid, but do when aqueous and molten. When they're solid, ions are locked in position and cannot move. When molten or aqueous, the ions are free to move through the structure, carrying the charge. Don't forget that. Question number 4. Right. Purifying copper. Guys, right. So we have got, they've said, we have got a student investigated copper electrodes. So both of the electrodes here are made of copper. Both of them are copper. And in the beaker is copper 2 plus copper sulfate. It then says she uses this method, weighs the 2 clean strips, uses one as positive, one as negative. Fine. After electrolysis, she washes the strips in ethanol and they quote some data. And then she dries the strips afterwards. The positive electrode, here's the half equation. Oh, I hate that. It should not be like that, folks, but Edexcel and their infinite wisdom, hate them. Copper goes to copper 2 plus +2 electrons. Please don't ever do this, folks. No. Edexcel are idiots. So just watch out. Should be on the other side, but you're allowed to do it. It annoys me. On the other side, it gains them. Suggest why the copper strips dry more quickly when washed with ethanol than water. Ethanol has a lower boiling point, so it evaporates more easily. We're done. Next, work out the difference. So it says calculate the increased mass of the negative electrode. Right, so I do a bit of maths. 8.25 minus 7.95, and I get 0.3. Guys, how many people missed that 0? Notice, they both are to 2 decimal places. Therefore, they must be to 2 decimal places as their answer. And everyone misses it because their calculator will make it vanish. Do watch out, folks. Be careful. The copper is removed when washing or dried. When she washed it with ethanol, she's going to wash off the copper. And the other one is the positive electrode is going to contain copper, always contains impurities, which means some of the mass is going to be lost. We're going to lose more on the positive electrode because some of the mass is going to drop off as sludge, and that sludge won't go onto the negative electrode, therefore it won't increase as much as the positive decreases. That's hard. Next, plot a graph. So I plotted the graph, took ages, circled my anomaly, showed my lines up for their answers and read my graph. Right, suggest why the straight line should go through the origin. Because this question here, I had to really think about. I was like, what? Why does it have to go through 0? It goes through 0 because if I don't apply an electrical current, I'm going to get no increase in mass. And that turns out to be the answer on the Mars scheme. I did take a little bit of a stab in the dark about that, folks. That was hard, that. I nearly got it wrong. Next, explain why the graph shows the increase in mass to be directly proportional. It is a straight line through the origin. They're asking you to define directly proportional. See graph, 17.6. Next, and look what appears again. Explain what is member to electrolysis. Split a compound using electricity. We've got our products. Why does it need to be molten? To allow the ions to be free to move. Write the ionic half equation for the formation of chlorine. Seen that over and over again. And that, folks, brings us to the end of electrolysis and ionic bonding. Before I go, I am aware that I haven't done aluminium. Aluminium, number 1, the ore, a rock that contains metal, enough metal to be worthwhile extracting. The ore is called bauxite. Metal ores. That is put in a container. So that goes in along with cryolite. Cryolite has one role: reduce the melting point, MPT. You then have graphite electrodes. You have black graphite electrodes. And these electrodes, this here is the positive electrode, which means I'm going to have the O2 minuses. This is what I've got in the mix. And of course, this is the positive electrode, which means this is going to go over to here. The oxygen oxide will form oxygen. Double it, 4 electrons. And I'm going to make oxygen gas, but I don't see it. The reason being, this is at 1000 Celsius, which means the carbon electrode, which is graphite electrode, reacts with the oxygen at this temperature, forming CO2. What that means is the electrodes get eaten away. They get eaten and eaten and eaten until they need to be replaced. One of the biggest costs of aluminium extraction is the replacement of the graphite electrodes. That brings me to the very end, folks. I'm done at that point. Let's bring you guys back to me. Or in fact, maybe me to you. Let's have a look. So I can go stop sharing. Hey guys, it's 8:30. Thanks so much for hanging out with me. I know it was a little bit longer than usual. I asked Miss all day and she was like, that's A level, but I'm kind of curious now. Lucas, you're more than welcome. Amira, so very welcome. Sarah, very welcome. I hope it's been useful. I'd definitely say it's worthwhile watching back. It's a tough one, this one. It's one of the hardest topics there is in GCSE, and everyone finds it hard. Guys, you know, if you've got any questions that you find on the exams, you know I will always give you my time. Always. Come and find me. I'll help you out. Guys, I'll see you next week. No, reminder, it's not happening next Tuesday. It's happening next Wednesday. Guys, have a really good evening. Thanks so much for coming, and I'll see you soon. Night, guys. Bye.